Hi everybody. So today I wanted to talk about Chapter 4 on forces in motion. And first I'd like to define forces. Forces are pushes or pulls. That's basically what they are. They cause any change in the velocity of the object. Anything that causes the object's velocity to change is a force. And that's Newton's definition of a force. Forces act on objects and they require an agent or a cause. So you have to have something causing the force. They're vectors, which means that they have magnitude and a direction, so they're directionally dependent. There's a couple of types of classes of forces. There's contact forces and field forces. Contact forces, they involve physical contact between the two objects. You have to be touching, in other words, the two objects must be touching in order for the force to happen. This would be like a punch or a push or pulling on a rope, or here we show the horse where it's hooked to a harness, which is pulling on the rope, which pulls the cart. Okay, so all those things are touching. Field forces, though, they don't require physical contact. So a common example of a field force might be the magnetic force, where you have a magnet that is pushing or pulling on another magnet, or a metal that's magnetic. Okay, so there you can see the force even when the magnet isn't physically touching the object. For example, here the magnet pulls the paper clips to the magnet without even touching it. So those are the two types. There's four fundamental forces in nature: gravity, the electromagnetic force, the nuclear force, and weak forces. These are all field forces. It turns out all forces, even contact forces, are caused by these field forces. So what you think of as a contact force, for example, I feel a force when I push my two hands together here, that's really at its root an electromagnetic force, where the electrons in this set of my hand and the electrons here are repelling one another, and that's what prevents my hands from sinking into one another and the skin merging. Okay, so it's really electromagnetic at its heart. So that's where all forces come from, those four fundamental forces. Now, a long time ago, Aristotle, and this was before the Common Era, believed that a force was always required to keep an object moving. And that's just based on our sort of everyday kind of common sense. If you give something a push, right, it'll eventually stop moving. So it'll go for a little bit and you'll accelerate while you're pushing it, but as soon as you stop pushing it, it'll eventually come to a stop. So that's why Aristotle believed that, okay? What we know now, of course, is that the reason that things come to a stop eventually is because of dissipative forces like friction. If you were in outer space, though, a perfect vacuum, and you weren't near any objects and you gave something a push, it would just keep going. Nothing would be there to stop it. And this was the world envisioned by Galileo. Okay? Galileo envisioned a world without friction, and then the objects would move at constant velocities. Once they're given a push, they keep going forever, even without an external force. So the equations that we're going to discuss in this chapter and the formulations for force and our conception of force were laid down by Isaac Newton, Sir Isaac Newton. He's famous for a lot of different things. He formulated, first and most importantly for this chapter, the three basic laws of mechanics that are known as Newton's laws. In addition, we'll study later, he discovered the law of universal gravitation, which explains why, for example, the moon and the earth are attracted to one another. He also, in order to explain the physics, invented a form of calculus. He did this simultaneously with Leibniz. And he did a lot of work on light and optics. All of Newton's laws are valid for what we call inertial frames. Okay? Inertial frames of reference or inertial coordinate systems are ones that aren't accelerating. Okay? Newton's laws are going to be valid for inertial frames or non-accelerating reference frame. So any reference frame that moves with a constant velocity is an inertial frame. So even though it's moving, it's still okay. All right? If you want to get really picky about it, then the Earth isn't really an inertial frame, all right? Because we're in an orbit about the sun, okay? And so we're moving in a circle, so we're constantly changing direction. So we're not truly an inertial frame, but we're a good enough approximation that you can use the Earth as an inertial frame for your problems in this chapter. So there's definitely some non-inertial frames, frames that are accelerating. In the pictures, I show a couple of them. So here this little girl, she's on a turntable, okay, at the park, and she's definitely in a non-inertial frame. She's accelerating like crazy. So the laws of physics would look different to her. If she tried to roll something straight, for example, along her reference frame, it wouldn't. It would curve off. So to her perception, there would be all these weird, crazy forces. This guy in the car is another example. To him, he's just cruising along until something happens. The brakes get slammed on, or the guy speeds up a lot. And then to him, from his perspective, his coffee just miraculously jumps out of the cup and it spills all over him. Okay, so these are examples of non-inertial frames. So for the Newton's laws to be valid, they have to be non-accelerating or inertial frames, and then these will work just great. So let's move on to Newton's first law. There's 3 laws, and the first law is, in the absence of external forces, an object at rest will remain at rest, and an object in motion will continue to be in motion with constant velocity. Okay? Object at rest stays at rest, object in motion stays in motion. You might have heard of this already. But basically, it's just kind of describing what happens in the absence of a force. Okay? If there is no force, in other words, there is no acceleration. If there's no acceleration, then the speed doesn't change. So if the object is still, it'll stay still. And if it's traveling along at a constant velocity, it'll remain at that constant velocity. This is also called the law of inertia. Okay? And inertia is an object's resistance to change. Newton's second law says that when viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay? Force is the cause of the change in motion as measured by the acceleration. What this means mathematically is that if you sum up all the forces that are acting on an object, then the sum of those forces will equal the mass of the objects times the acceleration of the object. Okay? So the sum of the forces is equal to ma. That's Newton's second law. So I want to emphasize that this is the net force, which means it's the vector sum of all the forces acting on the object. Okay? So if I have my cup here, I've got gravity acting down on my cup, but my hand is holding it in place, so I'm exerting a force upward on my cup. Right? I have to flex my bicep a little bit to hold the cup up. I have to exert a force upward. Okay? And then the cup will stay still. So the sum of the forces here is equal to 0. Down for gravity, up for my hand, and the result is no net acceleration. So this emphasizes the vector direction, the vector nature of the force. So just like in our chapter 3 stuff, where we're breaking our kinematics equations into the x equations and the y equations, vectors are going to have components too. Okay? So what that means is that you'll have independent equations for each direction. So the sum of the forces in x has to equal the mass times the acceleration in x. The sum of the forces in y has to equal the mass times the acceleration in y. Okay? And etc. Okay? So each one of these will have its own set of equations. The directions are independent of one another. Okay, so we're moving into a new unit. The SI unit of force is going to be called the Newton in honor of Sir Isaac Newton. The abbreviation is a capital N. Okay, it's a derived unit. In order to get a Newton, you have to multiply a mass times an acceleration. So the units of mass are kilograms, and the units of acceleration are meters per second squared. So 1 Newton is going to equal to 1 kilogram meter per second squared. Now, if you're to switch over to English units or U.S. customary units, instead of newtons, you're going to have it in terms of pounds. So pound is a unit of force, all right? And in English units, I love this, it's so funny, 1 pound is equal to 1 slug times feet per second squared, because the slug is the English unit of mass, all right? Which you've probably never heard of. If you trade over in units, 1 newton is about equal to 1/4 of a pound. So the newton is bigger than a pound. Okay, so the tendency of an object to resist any attempt to change its velocity is called inertia. We measure inertia through mass, all right? Mass is the property of an object that specifies how much resistance it has to a change in velocity. You've probably experienced this. It's much easier to push a light car than it is a heavy car. So it would be a lot easier to push like a Ford Fusion than it would be to push one of those large SUVs, okay, because they're a lot less massive, the Fusion is. So what that means is that for the same force exerted, more massive objects are going to have lower accelerations because they're going to want to resist that change more. And you can set this up as proportionality, okay? Masses can be given in terms of the accelerations that are produced by a given force. So for the same force, you'll get a higher acceleration for a lower mass object. Mass is an inherent property of an object. Okay, it's independent of the object's surroundings, and it should be independent of the method used to measure it, as long as the device is calibrated well. Mass is a scalar, and the SI unit of mass is the kilogram. Okay, so you might have had a minute of pause when I told you that the English or U.S. customary unit of force is the pound, because you're probably used to thinking of your mass, or how big you are, how much you weigh, in terms of pounds, and you think of that as sort of your mass. But really, there's a difference between the gravitational force and the mass of an object. So the gravitational force is the force that the Earth exerts on an object. Okay? It's how hard the Earth pulls it. This force is always directed towards the center of the Earth. So that's why the gravity is in the same direction, always down towards the center of the Earth, whether you're in the United States or China, right? It pulls towards the center of the Earth. So people's heads up are here in the United States, and they're this way in China, but to everybody else, it's just towards the center of the Earth. So from Newton's second law, if you plug in from what we learned last year, last chapter, the acceleration due to gravity is 9.8 meters per second squared downward. So that's our acceleration due to gravity here on planet Earth. So you plug that in for your acceleration in our force equation, F equals ma, and you get your gravitational force. We usually use g with a little vector symbol over it to mean the acceleration due to gravity here on planet Earth, 9.8 meters per second squared. So your gravitational force from Newton's second law is going to be F equals mg, okay? And the magnitude of that force is the weight of the object. Now, your weight can change. Your weight can vary with location. Okay, it doesn't change much, but as you go up in altitude, as long as you're still on planet Earth, it might change by as much as 1% or so, depending on how high up you are. Therefore, weight is not an inherent property of the object. Okay, you can extend this logic to other planets. So you might have seen videos of astronauts on the moon. Okay, and they look like they weigh a lot less, because they do, because the moon is smaller, because the acceleration due to gravity on the surface of the moon is way less than the acceleration due to gravity on the surface of the Earth. So astronauts really do way less on the moon, even though they have the same mass in both places. Okay? So if you compare your weight on the Earth to the weight on the moon, it's about 1/6. Okay? So if you weigh 180 pounds on Earth, then you weigh about 30 pounds on the moon. So you can lose weight by going to another planet, but that's not going to change how your pants fit, okay? If your mass is 70 kilograms here on Earth, it's going to be 70 kilograms on the moon too. It's the acceleration that changes. So the mass doesn't change, and the acceleration does change. Okay, so for an example of that, here's an example problem. A woman has a mass of 55 kilograms here on Earth. What's her weight while standing here on Earth, and what would her mass and her weight be on Mars, where the acceleration due to gravity is 3.76 meters per second squared? So the answer is her mass is going to be the same on Mars and on Earth, and that mass is 55 kilograms. Now, the weight is different. You can calculate her weight here on Earth, and it's going to be equal to mg, or her mass times the gravitational acceleration, 9.8 meters per second squared. If you multiply those two numbers together, you get her weight is 539 newtons. Her weight on Mars would be different, okay? Her weight on Mars would be her 55 kilogram mass times her acceleration, 3.76 meters per second squared. And if you multiply those things together, you get 207 newtons. Okay? So she weighs less on Mars than she does on Earth, although her mass is the same. I want to do another example problem using Newton's second law. Okay? This one concerns horizontal motion and not the pull of gravity. So you have a 1,500 kilogram car, and it has a net constant force of 2,300 newtons acting on it horizontally. So what's its acceleration? And if the car starts from rest, what's its speed after 5 seconds? All right, well, here you have a net constant force acting horizontally. Let's take the direction of the force as the positive x direction, okay? Now we have to break our force into its components. So if the force is horizontal, then it's 2,300 newtons. So we'll say that the force in the x is plus 2,300 newtons. It acts in the positive x direction. To solve for the acceleration, we use Newton's second law, F equals ma. So here, 2,300 newtons is equal to the mass times the acceleration, which is 1,500 kilograms times the unknown acceleration, a sub x. And if you solve, dividing 2,300 by 1,500, you get an acceleration of 1.53 meters per second squared. So that's our acceleration. Now, assuming that car starts from rest, you can use the kinematics equation. The final velocity is equal to the initial velocity plus the acceleration times the time. If you use that, then you can plug in there. If we start from rest, our initial velocity is 0, plus our acceleration, 1.53 meters per second squared, times our time, 5 seconds, and you get a speed of 7.67 meters per second after 5 seconds. So this brings up an important point, the last point that I want to make in this video lecture. If your force and your mass are constant, then that means that you're going to have a constant acceleration. If you have a constant acceleration, then you can use your kinematics equations. So there might be some problems in this chapter that combine using F equals ma, or the sum of the forces equals to the mass times the acceleration, and then using that to solve for the motion of the particle like we did in that previous example problem. If that's the case, you just fall back on those kinematics equations from the previous chapters and solve that way. Okay. So hopefully that helps you out, and I'll see you in class.